All right, everyone. Hope you had a good weekend. I graded your mini exam 5s yesterday and posted the grades. They were pretty good. Mini exam 6 is supposed to be due when? 28th? Yeah, but I said I might have to push it. So let's see how today goes. I still may push it regardless. I might push it out to like Friday or something. We'll see. See how today transpires. Okay, we ready? Here we go. So we've gotten to a very, very nice result. It's one of the more important theorems in this class. It's called the Greens Theorem. There's an entire section dedicated to it. And so before I can start it, I need to define something for you first. So whenever we have a closed curve, okay, a closed curve, that means it's a curve that starts at a point, ends at a point, right? Same point. So it starts somewhere, goes around, comes back, and terminates here also. So that's a closed curve. Positive orientation means that we are traveling along that curve in the counterclockwise direction. All right. So that's what positive orientation means. Negative orientation would mean clockwise traversal of the curve. So that's just some language. Now, what is Greens theorem about? Greens theorem amazingly connects a line integral around a simple closed curve to the double integral over the region bounded by the curve. So a line integral is one thing. A double integral is something else. Greens theorem connects the two together. So let me get to the theorem. This is it right here. It says, let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. It says, if P and Q have continuous partial derivatives on an open region that contains D, that just means that the partial derivatives exist within the region we're talking about, then the line integral over C of P dx plus Q dy is equal to the double integral over D of the partial of Q with respect to X minus the partial of P with respect to Y with respect to area. Now, I'll explain this in a minute, but some notation. That circle around the integral sign lets you know that that C is closed and positively oriented, meaning counterclockwise traversal of the curve. If for some reason we need to go the other direction, we can use this symbol with a little arrow that shows that it's clockwise instead of counterclockwise. Okay, so we get straight into an example, but I just want you to all understand before we get into this example, this integral right here, we actually have done this in the previous sections, and I'll show you in our notes. It was basically these two notes. When we were trying to calculate work earlier, we said that we had a vector field. Let's see, for a two-dimensional vector field, work is f dot dr, which turns out to be the line integral over C of P dx plus Q dy. And then in 3 dimensions, it's this, but we are focusing on this right now. Okay, 2-dimensional. So, Greens theorem is going to allow us to, oops, wrong one. Greens theorem is going to allow us to do line integrals with double integrals instead. Okay, so let's look at this first example. And I'm going to just copy this real quick. So the instructions here to evaluate this line integral, and it says to do it using both line integrals, previous sections, and then use Greens theorem. So I'm going to do it both ways. So let's do it the way that we normally would do this problem, okay? So the way we would normally do this problem is we would look at the curve C, which is the unit circle. And we would try and come up with parametric representations of this circle. So I can draw this circle if I let x be equal to cosine t, and I let y be equal to sine t. I apologize, I'm all congested today. Allergies are terrible. T is going to go from 0 to 2 pi, so this should draw me a unit circle. We should all be comfortable with that. Then we look at dx dt, that's negative sine t. We look at dy dt, this should be cosine t. And now we just go and do this line integral, which should now be the integral from 0 to 2 pi. And then I'm gonna do these separately. So I'm gonna do this one first, and then I'll do another integral like this. So I put in y, and y for us in this curve is sine of t. And then times dx. dx is right here, so we get negative sine t dt. So that's my first integral. Then I say minus, now I have a new integral, 0 to 2 pi. X here is cosine t. And dy is the derivative over here, which is cosine t dt. Now, both of these have the same limits of integration in the same variable, dt. So I'm going to make this one big integral. I'm going to factor a negative out of both of these, which will make this sine squared t plus cosine squared t dt. And that's just 1. And if we do the antiderivative there, we get negative t evaluated from 0 to 2 pi. And so we should get negative 2 pi. Okay, that's the way we do that problem before Greens theorem. So Greens theorem says this: if you want to do a line integral over a positively oriented closed simple curve like this is, if we have positive orientation, drawing the circle like that, instead of doing that line integral, we can look at the region that it encloses. Call that region D. And the theorem says, bring up the theorem here, get up here. The theorem says this, that we can do this by calculating the double integral over D of the partial of Q with respect to X minus partial of P with respect to Y dA. Now, P and Q here are the two functions, scalar functions that were up in our original integral. So here, this y would be p, and q would be x. Sorry, negative x. Be careful, because that minus sign here has to carry with the x. So that's your p, and that's your q. So now let's plug this into the formula here. Let me write this down here. P was y, and q was negative x. So if I come over here, this will become the double integral over D of the partial of Q with respect to X, which is -1, minus the partial of P with respect to Y, which is also 1, dA. Y'all with me? Now this is just -2, so I'm going to pull that out of the integral. I have double integral over D of 1 dA. And who's going to make me happy and tell me what that double integral really represents?
The area of D.
The area of D. And guess what? D is a circle, right? And we know the area of this circle should be pi times the radius squared, but see, it's the unit circle, right? So this should just be pi, shouldn't it? That should just be pi. And so we don't have to do any computations right now. This just becomes -2 pi, and we're done. And they match. What do you think? That's pretty cool, right? You must have a closed curve positively oriented. It must enclose a region D. Now we got lucky because the region D was a circle and our integral at the end was the double integral of 1 dA, which meant the area of the circle. It won't always turn out that way, but when it does, it's nice. Now, I would argue that the work we did here wasn't that bad. Like, this isn't terrible, right? So you could argue both ways, or, you know, almost equal work. I don't know. But how about the next example? How about this one? Same thing. I want to do this both ways. So let me take a look at C first. Well, C is a circle, right? X squared plus y squared is 9. And it has a circle of radius 3. So I could do it the good old-fashioned way, which would be to find parametric representation of the circle. So 3 cosine t, 3 sine t for the x and y respectively. I can restrict t between 0 and 2 pi. I can get the derivatives of these. But now do you see what's going to suck? Do you see what we're going to have to do here? Integral 0 to 2 pi, 3 times y. So 3, let's see, y is 3 sine t. So 3 times that is going to be 9 sine t minus e raised to the sine of x. So sine of x, but x is 3 cosine t. All of that times dx, which is negative 3 sine t dt. That takes care of this part. Now I have to do that part. So another integral, 0 to 2 pi, 7 times x. So 7 times 3 cosine t, that's 21 cosine t, plus, that's supposed to be the square root of y to the 4th, which is going to be 3 sine t to the 4th power. That's 81 sine to the 4th t plus 1. All of that times dy, which is 3 cosine t dt. Does anybody feel like integrating this? No. In fact, I put it into Wolfram Mathematica and it couldn't do it. But then when I went to Wolfram Alpha, the website, oh, I don't have it up anymore, but I did it on Wolfram Alpha and it actually did it. I was surprised. So my computer couldn't do it, but the Wolfram website could. But by hand, this would not be something we could do. I'm pretty sure we get stuck. But because this is a closed curve, because it's positively oriented, I can look at the region that it encloses, D, and I can do the double integral over that region of the partial of q with respect to x minus the partial p with respect to y. So I can bring this formula in again. I'll just do this. Are there any questions? Can I use this instead? Now, for us, P is all of this, and Q is all of that. And look at this. If we do this, double integral over D, what is the partial of Q with respect to X? So the partial of this with respect to X is just what?
7.
7. Okay, so 7 minus the partial of P with respect to Y, which is just
3.
Right? dA, and holy crap, we got another constant, didn't we? I can pull that constant out. 4 comes out. This is the area of that circle. That circle has a radius of 3 this time though, right? So the area of that circle should be pi r squared, it should be 9 pi, shouldn't it? So this should be just 9 pi times 4, the 4 we pulled out, so 36 pi. We're done.
Quick question, for P or assigning P and Q, does it matter
Yes.
which one we can assign it to?
Yes, P is always the one in front of dx and Q is always the one in front of dy. So we're using this right here.
Oh, okay.
That back later on, when we look at these as vector functions, P is always the one in front of dx and Q is always the scalar function in front of dy. So if you switch them, if you just choose them on your own, it won't work.
Okay.
Yeah, like if you did Q dx and P dy, the theorem would fail. Okay, so I hope first example, I showed you, hey, this is how we do it, but you know, the work wasn't that different. I mean, it wasn't too much more work to do that. This one should have convinced you, hey, look, yeah, like this would be almost impossible for us to do by hand, but Greens theorem allows us to still do it. All right, let's look at another one. Okay, so we can see that sometimes computing a line integral over a closed curve is easier when we use Greens theorem and convert the problem to a double integral. There are other cases where we can convert a double integral into a line integral. So if we have a line integral with P and Q in it, and as long as the curve is closed, we can convert that into a double integral, but the double integral part has these partial derivatives in it, doesn't it? So if someone were to just give us an arbitrary double integral, the only way we could convert it to a line integral is if this in here somehow looked like partial Q with respect to X minus partial P with respect to Y. Then we could transfer this into a line integral over a closed curve. Does that make sense? So from right to left, that we just did a bunch of. The only way we can go left to right is if somehow the integrand can be viewed as the partials, these partials subtracted. And that's a little bit problematic because we don't just have a general way of doing it. It's only specific cases. But there's one very interesting case, okay, the most interesting, and that is whenever we're trying to find the area of some region D, we already know this, that's the double integral over D of 1 dA, right? The question would be, is there any way that we can look at the number 1 as somehow being that part of the Greens theorem, this piece, partial Q with respect to X minus partial P with respect to Y. Like if that equals 1, then that would be this area integral. So the question becomes, what P and what Q would you have to have in order for this thing to turn into a 1? And there's 3 general cases we can look at. So if I let P be 0, okay, so let's say the P function is 0 and the Q function is X, then do you all agree that the partial Q with respect to X is 1? And the partial P with respect to Y would be 0? And then that would give you a 1. Which means that this area, this double integral, can be converted into the line integral over the closed curve that encloses that region D of X dy. Or you could do it another way. You could let the P function be negative Y and the Q function be 0. That derivative, this thing right here would still give you a 1, and the line integral would become this. And then there's another way right here, but I'm not even going to talk about that way right here. And there's actually not just 3, there's like a bunch of different ways you can do it, but the first 2 are the ones that are the easiest and make the most sense to work with. So let's see this in action. We're going to go back to something very basic, but I think something that all of us can appreciate. We want to find the area of a circle of radius r. Okay, so if I have a circle of radius r, can I find its area? Right? Can I find this area? Well, we all know now, so we're acting like we don't know the formula of pi r squared. Okay, act like you don't know that. All right, can we somehow verify it? Well, what I know is if I call this d, the area of d is going to be the double integral over d of 1 dA. Now, again, we're going to act like we don't know that that's pi r squared. But because this is a double integral and we have a 1 in here, and only because we have a 1 in there, I can convert this into the line integral over the closed path C of, now we have two choices that I really think you should look at, but ultimately we have more than 2. I want us to look at this one right here, this first case. So this area, or this double integral, will be equal to the line integral over the closed curve C of x dy, okay, of x dy, of x dy. Now, what do we mean x dy? Well, you have to now convert this into the path C. Okay, so C is the path that encloses that region D. And so how can you draw that path? Well, we know how to do that. X is going to be something and Y is going to be something. What are the, what's the parametrics for drawing a circle of radius R? What would they be?
X equals cosine of t and y equals sine of t, and it's bounded between 0 and 2 pi.
You put
Yes,
R in front of it.
Yeah, you got to have the R in front. You
Oh.
were drawing me the unit circle, but we want a circle of radius R, right? So t goes between 0 and 2 pi. Dx dt is negative R sine t, and dy dt is R cosine t. Y'all with me? Y'all with me?
Yes.
Okay, so here we go. We are now going to go line integral 0 to 2 pi. X is the R cosine t times y, dy is R cosine t, dt. Okay, R is a constant. I'm going to pull the R out. We actually have R squared, 0 to 2 pi. We have 2 cosine t's, so cosine squared t. And from Cal 2, I'm sure you all remember that you use power reducing formula on that to integrate this. So I rewrite that as 1/2 1 plus cosine 2t dt. You might remember that formula is this formula also. I just pulled the 2 off the bottom as a 1/2 out front. So this is going to be 1/2. I'm going to bring that out with the R squared, integral 0 to 2 pi. And then we have the antiderivative 1 plus cosine 2t dt, which is 1/2 R squared. Okay, what's the antiderivative of this? Antiderivative 1 is t. And the antiderivative of cosine 2t, be very careful, is 1/2 sine 2t. And we need to evaluate this from 0 to 2 pi. Any questions? We're almost there. Okay, let's just get this out of the way. When we plug in 0, everything's gone, right? When we plug in 2 pi, this becomes 2 pi here. plus, now sine of 2 times 2 pi is sine of 4 pi, but sine of 4 pi is 0. And so you get 1/2 r squared times 2 pi. The 2's cancel, and you're left with pi r squared. There we go. We have just verified that the area of a circle is pi r squared. Taking a double integral that we acted like we didn't know, converting it to a line integral, and then computing.
And that would have also worked if we chose a different formula for our line integral, like y dx. Sorry, was it negative y dx?
Negative y dx. Oh, we could use it for x dy. Are you asking me, would we have gotten the same answer had we used this one here instead?
Yes.
Yes. If we did this integral instead, negative y dx, we would have got pi r squared.
Okay, just making sure.
So really, we can do this for any area of any region, right? It didn't have to be a circle. It could be anything. Like, how about this one? Find the area of the figure below, an epicycloid, given by the parametric equations, x equals 5 cosine t minus cosine 5t, and then y equals 5 sine t minus sine 5t on the interval 0, 2 pi. So if you were to graph these parametrics, you would draw this really cool epicycloid, okay? That's what you would draw. And what I'd like to know is what is the area of that region. Now I can tell you right now, you have nothing, okay? Like you don't have anything. You have no calculus that you can do this with because that is not a function of x, right? This blue curve is not it fails the vertical and horizontal line test. There's no way you're going to be able to get this easily by doing some double integral over d of 1 dA. You can't do that. If this is d, you can't do that because you don't know anything. It's not making sense. Like you're kind of stuck. You're stuck. But the beauty of Green's theorem is that if we just travel along this curve, right, we can do it. We can convert that into the closed integral over the curve C of x dy. Which means all we have to be able to do is take the derivative of that, right? That's x. And we have to be able to do did I just say derivative of that? I'm sorry, I didn't mean it if that's what I said. We just have to be able to plug x in right there and then take the derivative of that and plug it in here, right? Take derivative. And then hope we can integrate it, okay? We have to be able to integrate it. Understand? I don't know, I've been teaching this forever. I still find this to be absolutely amazing that you can find the area of some weird region as long as you can do the line integral around it. It's very strange. All right. We're gonna do this. I don't know if we're gonna do the whole thing, but we're gonna at least set it up. So if I want to know that area, someone has already given me the parametric equations. So we're ready to do it. I'm gonna do line integral over the path C. Well, you know what? Of x dy, I'll write it, which should be the integral from 0 to 2 pi. Okay, x is gonna be 5 cosine t minus cosine 5t. And then dy, so I just need to take derivative of this, which is going to be 5 cosine t minus 5 cosine 5t. Be careful there, chain rule, dt. And then I can FOIL this out. Okay, so this would be 25 cosine squared t, that's here to here, and then here to here, minus 25 cosine t cosine 5t, and then here to here, minus 5, and that's another cosine t cosine 5t. And then last one from here to here, we should get a plus 5 cosine squared 5t dt. So oh, you know what, there's one more thing. These two can come together to give me negative 30 cosine t cosine 5t. Okay, so look, at this point, I'm going to stop, okay? Because we could do the rest by hand. It's not an easy integral, but it's by no means impossible. This one right here, I could do power reducing, right? This one right here, I could do power reducing. So I should be able to handle those. This one is a little bit harder, but what I would use for that is I would go to my formulas back from pre-cal. They're not in here. There's a formula for trig functions. Do you remember the sum to product, product to sum formulas for trig functions? Sum to product, product to sum. I don't want to bring it up because it can take too long. But we have a way to take a product of two trig functions and turn it into a sum. So you would do that, use that formula, turn this into a sum of two, and then do each of the integrals individually. But in order to save time, I'm not going to go through this work. I had the computer do it for us. And the answer is 30 pi. The main idea here is that we can do it. All right. All right, here we go. Another problem. Time to calculate work. So how is this related to what we're doing right now? We're doing work. So we want to calculate the work integral where our vector field is this and C is this triangle. So let me just first draw our triangle. So our triangle is this curve C. It's actually not a curve, it's straight lines, but starts out at 0, 0. It goes to 2, 6. And then back to 2, 0, and then back to 0, 0. So it goes like this, down, back over, and we're traveling in this direction. So C is closed, right? C is closed. I also want to realize that this work integral really means the line integral over C of P dx plus Q dy. And that was that note that I showed you earlier, this right here, that if we have a vector field PQ, then this is equal to this. All right, so I'm using that right now. And here for us, here's P, and here's Q. Now look, pay attention, this is very important. I have two options on how to do this. I could just do the line integral like we did last class or previous classes. What it would take is me breaking it up into 3 paths. So if this whole path is C, I would have to break it down into maybe like C1, C2, C3. I would have to find a parametric representation of that line segment, another parametric representation of that line segment, another parametric representation of that line segment. So basically that would become that over C1 plus that one over C2 plus that one over C3. And then, you know, I have to do all this computation. You understand? that would be a very long process, but we could do it. But because this is a closed path, right? This is a closed path, we should be able to use Green's theorem. There is one problem though. Do y'all see what the problem is?
Clockwise.
What's that?
Clockwise.
Yeah, it's clockwise. And Green's theorem only works if it's positively oriented. So what I'm going to do is this. This integral over C, okay, of f dr, okay, what I'm going to do is I'm going to say that that's equal to the negative of that over negative C of f dr. And see, the thing is, if you take the opposite direction, you just get a negative. Now, this opposite direction will be a positively oriented closed path, right? Negative C, C goes in that direction, right? So negative C would go the opposite way, right? Around that. So what I'm going to do is we want to know this clockwise orientation. So what we're going to do is we're going to take the negative of the counterclockwise orientation. All right, so that means I can use Green's theorem. So this becomes negative integral of p dx over negative c, sorry, p dx plus q dy, right? But that equals, by Green's theorem, negative double integral over d of partial q with respect to x minus partial p with respect to y dA. And here D is the region that is enclosed. That's your D. Any questions? What is the partial of Q with respect to X? What's the partial of Q with respect to X?
Two x plus 2y cosine x.
2x plus 2y cosine x. So 2x plus 2y cosine x. Then we subtract from that the partial of p with respect to y. So here's p. Take derivative with respect to y. We should get 2y cosine x dA. And do y'all see how nice this is? You see if those cancel? So now we have this negative double integral over d of 2x dA. Now look, we cannot do like we did earlier and just be like, oh, this is just the area of D, okay, because we have an x in here. But we can do this double integral. We're back to the beginning of this section. We're doing a double integral over D of a scalar function where here's our region. That is a type 1 region. And I hope that it's easy for you to see, I hope that it's easy for you to see for this region, X is stuck between 0 and 2, 0 to 2, and the Y values are stuck between the ground, 0, and this line right here. And this line has the equation y equals 3x because the slope is rises 6, run is 2. So this should just be 3x there. So that means this double integral becomes negative. Let's see, 0 to 2 for the x restriction, 0 for 3x for the y restriction. And we're integrating 2x with respect to y, then x. Y'all doing all right? Okay, antiderivative of 2x with respect to y is 2xy. And we evaluate that y equals 0 to y equals 3x. Then we'll integrate with respect to x. So this equals negative integral 0 to 2. Okay, plug in 3x for y, and we should get 6x squared. Plug in 0 for y, we get nothing. And now we're ready for another antiderivative. So minus, what is that? Divide by 3. So 2x cubed evaluated from 0 to 2. And then plug in 2, you get 8 times negative 2, you get negative 16. And you plug in 0 and you get 0. So your answer is negative 16. Which, trust me, is much faster to do it this way than it would have been to break this into 3 paths and have to find parametric representations for each path, and then have to actually try and compute this up here. It would have been a disaster, trust me. So where, during a test and stuff, when are you going to know maybe use through Greens theorem? Like what kind of tips you off? Closed curve. I mean, that should be it, number one. Like you see a closed curve like this, and you're asked to find work over that, then I would be thinking maybe Greens theorem. Then what I might do is look at the partials, like a partial of this with respect to x, partial of this with respect to y, see if they're nice. Like if that, if you put them together, if it becomes something nice. Okay. We're just moving right along. Okay, I've been debating whether or not I should show you this or not, because it's going to take up time. The question, yeah, I'm going to do it. The question is, Green's theorem works if we have this curve around this closed region, right? But what if we have a closed region that has a hole in it? Is there anything that we can deduce from that? So I'm going to start this on a fresh sheet here. See if you follow me on this, okay? This is going to be weird. Just trust me, at the end of it all, we will have a problem we're going to do, and I hope it'll be worth our time. Okay, so let's say that we have a region that has a hole in it. And I'm going to call that D, okay? I'll make a copy of this because I might need it in a minute. All right, would you all allow me to draw 2 paths? One path that goes along the outside of D in positive orientation, okay? And I'm going to call that path C1. And then I'm going to draw another path on here that goes this orientation like this. Let me just make sure I wanted to, yeah, like that. And then that goes around the smaller one. I'm going to call that C2. All right, y'all with me? Just let me do all this, and then you'll see, you're going to see the end result, and it'll hopefully be like, oh, that's why we did all that. Okay, now I see why. Okay, so we have this region D, which is the space here with the hole taken out, right? And then I've drawn a positively oriented path C1 around the outside and a positively oriented path C2 around the inside. Now I'm going to do something else. I'm going to break our region D into 2 regions. So I'm going to cut it right here and right there. Okay, so I've cut it into 2 regions. So we have a region on top, which I'm going to call D1, and a region on the bottom, D2. So D1 is everything up here in yellow. And D2 is everything down here in green. So let's start with this. Do you all agree that D is equal to D1 union with D2? So if you take this set of points and this set of points, put them together, you'll have D. Do you all agree with this? The double integral over D of the partial of Q with respect to X minus the partial of P with respect to Y, dA, that should be equal to the double integral over D1 of partial Q with respect to X minus partial P with respect to Y, dA, plus the double integral over D2 of partial of Q with respect to X minus partial P with respect to Y, dA. In other words, if this integral exists, this double integral, then I can break it into two, right? I can break it into two. This one over D1 and this one over D2. Yes? Okay, now I'm going to ask you to look at another thing. This is going to start getting crazy. I want you to look at another path. I'm going to do this path in red. This path is going to go across the top. Shit, come on. Go here, go over, go up, back down and over. And I'm going to call that F, the path F. So do y'all see that the path F just goes around D1? Yes, and I'm going to orient it that way. Oh, sorry. So F goes around D1. And I'm going to have another path on the bottom. Oh, shit. Come back here. It's hard for me to put this path in here. Do y'all see this green path that goes around D2? And I'm going to orient that positive also. I'm going to call that G. Okay. Y'all there? Okay. So in terms of F, in terms of this path F that goes around D1, I'm going to break that up into smaller pieces. I'm going to call this piece right here F1. Now remember, we're going like this. We're going to go across, that's F1. F2 is going to be the piece that takes you all the way across down here like that. And then F3 is going to be this little piece. And F4 is going to be that little loop right there. And remember that the direction of all of these is like this, the red arrows.
You just wrote F2 twice.
I did. Yes, you're right. Thank you. That's F4. I'm gonna do the same thing for G now. I'm gonna call this piece right here G1, and that goes to the left, right? That goes counterclockwise, goes like this. I'm gonna call this G2 right here, this piece right here that goes from here over here. I'm gonna call this piece G3, and I'm gonna call this little hump right here, I'm gonna call that G4. Shit, I know that that's a mess, but. Okay, you ready? Here we go. Let's take a look at this integral. Do you agree that that double integral over D1 of these partials, right? That's Greens theorem. By Greens theorem, that's the same as the line integral over the closed path. Now, what is the path that encloses D1?
That's F.
That's F, right? That's the F curve. And then this will be P dx plus Q dy. Do y'all agree that that's what that is? Okay, what about this one? Plus, same thing, by Greens theorem, that's the line integral over the closed path that encloses D2. What encloses D2?
G.
G, okay, of G of P dx plus Q dy. But since these are line integrals over a path, F is made up of 4 different paths, isn't it? So I can take this and I can break it down into 4 paths. It can be the line integral over the curve F1 of P dx plus Q dy, plus the line integral over F2 of P dx plus Q dy, plus the line integral over F3. This is getting a little monotonous, right? Of that same thing, plus the line integral over F4 of that same thing. That's all of that. Similarly, that can be broken down into its 4 paths over G1, G2, G3, G4. And it's all the same thing, P dx plus Q dy, P dx, Q dy, add all those up. All right. What can y'all tell me about the line integral over F1 and G1 right there?
They're the same.
They're the same, but aren't they in opposite directions? Doesn't F1 go from left to right and G1 goes from right to left? But they're the same line integral, just opposite directions. And that means they're opposite in signs, which means when you add them, they
Cancel.
cancel. Okay, so F1 and G1 will go away. Any others go away?
G3 and F3.
G3 and F3 also cancel each other out because they're in opposite directions, but everything else is still there. However, do y'all see what the line integral over F2 and G2 create? If I go F2 followed by G2, isn't that really just the line integral over C1, the original path that went around, isn't it? So those two together is the line integral over the closed path C1 of P dx plus Q dy. Plus, now what about F4 and G4? What do those create? So F4 and G4. You got to pay attention to the direction here, everyone. Pay attention to the direction. Which way is G going? G's going counterclockwise, right? And F is going counterclockwise. So G4 and F4 together is going counterclockwise, right? Isn't it? But what path is that?
C2.
It was
The negative
almost
C2.
C2. It was almost C2. Hold on, let me see. Let me paste. Oh, I didn't have it there. Didn't I do? What did I do? I did C1 went like this, right? That's what I did. And then didn't I make C2 go the other way or no? I don't remember which way. I
You
made
did
C2.
not make it go the other way originally.
I didn't?
No.
Okay.
Yeah, it was the same way.
It was the same direction? Okay. So C2 went like that? Okay. So that is C2, isn't it? That is C2? So plus. Okay. There it is. We're finally to the end result. And I'll summarize it in a new picture. If we have some region D, right? And we have a path that goes around like this, C1. and another path on the inside that's also positively oriented, C2. Then we have that the double integral over D of partial of Q with respect to X minus partial of P with respect to Y dA must be equal to the closed line integral over C1 of P dx plus Q dy plus the line integral over C2 of P dx plus Q dy.
So this gives us the ability to find the area of regions with holes in them.
You could, you could, but that would have to be, this would have to be a 1, right, in here for us to do this? But you could, yes. Absolutely. The way we're going to do it, though, I'm now going to show you how we're going to use this. I want you to think about this, and I'm going to give you like 5 to 6 minutes, maybe even more, to consider this next problem. And I would invite all of y'all to talk. I'm not going to do breakout rooms. Just I would like for y'all to think about this one and maybe talk to each other about what's uniquely hard about this problem, what's different about it compared to anything else that we've done up to this point, and maybe figure out if y'all can come up with some idea of how we might. Well, I really want to see if you can get to the point where you realize like what's hard. That's really what, and then I'll show you how we can get it. So I'm going to give you about 5 minutes to talk about it.
So I'm thinking the first part that sucks about this is that it's actually, we're given the answer. We're given that it's already equal to 2 pi, but we're not given R, like, at all. So I'm guessing we gotta figure something out along those lines.
Isn't there a like some type of relationship with the at the denominator? Both denominators have x squared plus y squared. 'Cause I remember an old equation he showed was like 1 over the square root of x squared plus y squared, and then the y value, or that was for the x value, and then the y value was also 1 over square root of x squared plus y squared. I just don't remember if it was some type of shape or some type of line graph.
That was when he was generating a vector field F where the magnitude of every vector was the same. It was, what's it called? He was dividing each component by the magnitude. We're not dividing by a square root, so we're not dividing each vector by the magnitude, but it does share a common denominator. So that's probably going to help simplify things or play some sort of role.
Oh, okay, I see.
Yeah, I agree. I'm kind of zeroing in on that denominator of both of them too. Looking at, that's just a vector. It's a vector in the same direction. It just has a different, it's been multiplied by or divided by x squared plus y squared. But then you have the terms are, the first term is in terms of y or negative y, and the second term is be in terms of x. And so you have a mixture of the factors as well. When you start to integrate it, it's going to be a little bit of a mess.
So he's showing us that we don't need an R. That's what I'm
Right.
getting right now. And if we write this all out, we're gonna see that we have to remember that it's equal to 2 pi. And
So I have a very annoying.
Well, hold on, it's not equal to 2 pi. You have to show it's equal to 2 pi.
Well, I'm just saying, we know it's equal to 2 pi, but yeah, or I guess we don't know. We might actually find out it's equal to only pi and show that it didn't equal 2 pi.
Lost me on that one.
Right, it's kind of like a proof though. You can't really play with the 2 pi until you get to the very end, and it's just like, did you do it correctly so that you showed that the stuff on the left equals the 2
Exactly.
pi? Right,
Yeah, that's
Right.
correct. That's correct. So has anyone like has anyone like been able to figure out what is the unique difference in this problem compared to every problem I've done today or prior to today?
Mhm.
It's C.
C is not given.
C is
Yeah,
any
what's
closed
C?
path.
Any
Any closed path. Yeah, that's what I
closed
picked up
path
on.
enclosing the origin. So you could just come up with your own path, right? That encloses the origin. That just goes around the origin, and you could show it's 2 pi. But that doesn't show that it's for any, right? So how in the world are you supposed to check every single path? Right? Just because it holds for one case does not mean it holds for all. So I don't expect students to get this problem ever. This is one of those things that I want everyone to understand the challenge. You know, we have a P, we have a Q. Okay, we know we need to do this computation, but when it comes to C, we have to come up with a parametric representation of C, but C is arbitrary. So long as the path we choose encloses, we'll call it C. So long as the origin is in here, then any path that does that is valid, but it has to hold for all. That seems very hard, doesn't it? Very, very hard. Okay, so y'all ready to go after it? We are actually going to use what we just did. Okay, that's why I showed you everything I just showed you, is so that we can do this. All right, so let me grab this problem. This is one of my favorite examples out of everything we do in this class, because it's such a non monkey see, monkey do problem. It's one of those problems where it's like, wow, you really have to come up with this. I mean, and someone else did it. I didn't do it, okay? But I saw it. And once you see it, then you start thinking a little bit more like math people think. Okay, so here's the idea, is that if, let's say we have a path, okay, that encloses the origin, and it's arbitrary. So here it is. I'm going to call this C, and I'm going to orient it positively. And for the sake of ease, I'm going to call it C1. Okay, I'm going to call it C1 so it'll match the work we just did. All right, y'all good? Now, if it encloses the origin, can it touch the origin?
No.
It cannot. Okay, so we have to all agree on it. If it encloses the origin, then no matter how I draw it, there's going to be some space between the origin and any, like the closest point to the origin on this curve, there's some gap between there. Do you all agree? There's some little buffer. Okay, whatever it is, it's some positive number. So now I'm going to do something really clever. I'm going to choose A, which is just going to be a positive number, such that the circle with radius A is inside C1. Now, I should be able to do that because like you just said, there's got to be some buffer between the curve and the origin. So if I found that distance, the shortest distance, I could just take half of that and I would be inside. Does that make sense? I could let A be half that distance. So I'm gonna draw this circle in here that has a radius A, and I'm gonna orient it like this. Yeah. Now, we know that we can call that curve anything. Let's call it C2. See, is this starting to look like, this? Yeah. And we just determined from all the work that I just showed you that this is true. We know that the line integral over C1 of P dx plus Q dy plus the line integral over the closed path, C2 that was closed, sorry about that, of P dx plus Q dy, that should be equal to the double integral over D of the partial of Q with respect to X minus partial P with respect to Y, right? That should be true. So let's see, how in the world is that going to help us? Well, I don't know. Can we calculate these partials? Let's calculate the partials. Let's just see what they are. So I'm going to go back up here. Let me write down what P is, just so we have it. P is equal to negative Y over X squared plus Y squared, and Q is equal to X over X squared plus Y squared. So I know if I'm going to use this, I'm going to need that. Let me go ahead and calculate that. What is the partial? Let me do partial of P with respect to Y. I'll do that here. With respect to Y, I have to do quotient rule. So derivative of the top is 1 times derivative of the, times the bottom, minus the derivative of the bottom with respect to Y is going to be 2Y times the top all over the bottom squared. And if I clean that up, let's see what I get. Negative X squared, then negative Y squared, then positive 2Y squared, all over X squared plus Y squared. This looks terrible. And then I get negative X squared plus Y squared all over X squared plus Y squared. Okay. That all right for the partial of P with respect to Y? Okay, let's get the partial of Q with respect to X. Partial of Q with respect to X, same thing, quotient rule. Derivative of the top times the bottom minus derivative of the bottom, which is 2X times the top, X all over wait a minute, hold on. P with respect to Y, Q with respect to X. Yeah, I'm doing this right. Yeah, okay, so let's see, all over the bottom squared, which is, do y'all see what it is? What does all that become? Y'all are so shy.
Same thing.
I didn't hear you, Gregory, if you said something.
It looks like it's the same one as the other derivative.
It's the same as the other one. Aren't those the same? So if you take partial of Q with respect to X, that, and subtract the other one, which is exactly the same, what do you get? 0. You get 0, don't you? So that means that this side is 0 because the vector field, the partials of it just amazingly went to 0 for this particular example, which means that this line integral over C1 of P dx plus Q dy plus the line integral over C2 of P dx plus Q dy, those added together must be 0, right? Which means that they're equal to one another, but off by a sign, right? They're equal to one another, but off by a sign. So what I can say is that the line integral over C1 of P dx plus Q dy must equal negative line integral over C2 of P dx plus Q dy. Now, this is really good because we are trying to find, remember, we wanted to find C be any path, right, enclosing the origin. And for us, that was C1, all right? I called it C1 instead of C. And do you see that we actually have a way of doing that? We can find that integral, that line integral, so long as we can find this line integral. But what's good about this line integral in blue? What's the good news?
Isn't that one a circle?
Yeah, that's the circle we came up with, right? This is over C2. C2 is this guy right here. So now what I can do is I can look at C2 and find its parametric equations. So let's go back up. Here's C2. This C2 is, this is what C2 is. C2, x is equal to a cosine t, y is equal to a sine t, with t being between 0 and 2 pi. See, I can draw that circle all day long using a as the radius. Those derivatives are negative a cosine t and a cosine t. I wrote the wrong thing. Negative a sine t. And the derivative over here is this. Okay. Y'all still there? I need this. Okay, here we go. I think we're ready. We're trying to do this blue integral. This should be equal to negative integral from 0 to 2 pi. Okay, I need P. Now, what's P? This is P, but I have to replace y with a sine t, and then I have to replace the bottom with a cosine t here for x and a sine t. So on the top, I have negative y, which is a sine t, over, can someone tell me what the bottom really is?
A.
A squared.
A squared, right? X squared plus y squared, that's this one plus this one squared, and that'll give you an a squared on the bottom. Okay. That plus, now let's do the Q. Q is this one. So on the top goes X. X is a cosine t, all over the bottom, which is, again, right, a squared dt. What am I missing? I'm missing something. Hold on. I screwed up. Hold on. Back up. What am I missing? I put the P, right? Here's P. What was I missing next to it?
The dx.
Dx, I'm sorry. Dx, I forgot dx. There's next to it a negative a sine t. Let me just do that integral by itself. And then I'll do plus. Now I'm going to do this integral let's put that negative sign way out in front of everything. Let me do that negative sign here. So I'm doing this negative sign, then I'm doing this integral right here, plus this next integral, 0 to 2 pi. Now, we just said that the x, which was a cosine t over a squared, but then I need dy. dy is a cosine t dt. All of that like that. Okay, now it's going to work. Okay, do y'all see what happens? A squared, negative a, a squared. So this just becomes sine squared t. And then this integral is cosine squared t, and you can put the two together. So it'll become sine squared t plus cosine squared t dt, which is just negative. What do we got? Integral 0 to 2 pi of 1 dt, which should give you negative 2 pi. Now hold on, we're getting a negative. Where did I mess up?
You should have computed the yellow integral. C1, since you just solved for C2.
Oh, you know what? Hold on.
Well, no, we know that C1 is going to be the same as negative C2, so you're going to get 2 pi as your answer.
Yeah, but I thought I accounted for the negative right here.
I thought you just carried down the negative since you said that they were equal. You kind of just brought it down from the equation, that side.
They have to be equal to 0, right? This has to be equal to 0, so I moved one of them to the other side. C2 is positively oriented. Yeah, okay. Let's not, because we've already eaten up so much time. I'm off by a sign. I'll go back and look and see where I have the sign issue, and I'll just email y'all later. We got the 2 pi, right? So that problem, completely unnatural. You would never think to do this, but now you can see how you can use something that seems so useless to do all that work. And we actually just showed that the line integral over any path is going to be equal to 2 pi arbitrarily for this vector field. And we found it holds for any path without actually ever having to check every single path. It's pretty crazy. So, all right, we got 22 minutes. I'm going to move on to the next section because we need to. Let me just make sure I've done what I wanted to do there. Yep. Okay. Curl and divergence. So we're going to talk about vector fields again. So vector fields, when we first started out this chapter, we talked about how vector fields can be either 2-dimensional or 3-dimensional, right? I'm going to bring up 10. Get out of here. Just want to remind you before I get into this too much. Thought I had this open. Oh, wrong chapter. 13. Vector fields. Okay, so we had talked about vector fields. You know, at every point in space, you have these arrows, right, that show like a flow. Okay, so now what we're going to do is we're going to talk about curl and divergence. So given a vector field F, we now define two operations on the vector field. So two things we're going to talk about: curl of the vector field and divergence of the vector field. When we take the curl of a vector field, the result will be a vector. When we take the divergence of the vector field, the result will be a scalar. Okay, so these are really cool because it's very visual. So let's start with the curl. So if you're given a vector field, F is equal to PQR, and the partial derivatives exist, then the curl of F is defined here. Now you can try and memorize that. but there's an easier way to actually remember the formula for curl. And that is to use this really cool notation. Curl of f equals the gradient crossed with f. So we had this idea of a gradient. Okay, the gradient is the partial derivatives. So if you take the partial derivative with respect to x, y, and z, and look at them as a vector, which is kind of strange because they're not really vectors. But if you look at the partial derivatives as a vector, then we can define that to be this gradient. And then what you do is you cross it with the field. So you do your P, Q, R field down here, and then you do the determinant. Remember how to do determinant? You to find the I, you cover this up, and then you multiply across here, subtract what you get when you multiply there. That right there is this. And then you do the same thing, you cover this up, and then you do those two multiplied minus those two, but then you change the sign. And then you do cover this up, and then you do multiply here, subtract, multiply there, and that'll be this piece. So I'm going to take you through an example. This thing right here, this gradient thing is called a differential operator, okay, because it does an operation on a field. So here's a, just so we can make sure we understand how to calculate the curl. Then we'll talk about what it means visually. Okay, so find the curl of this vector field. So we have a vector, this is P, this is Q, this is R. So if I want to do the curl of F, I need to take the differential operator and cross it with the field, which means I'm going to do the determinant of this I, J, K. I'm going to take the partial with respect to X, partial with respect to Y, partial with respect to Z, and cross that, or find the determinant there with, or cross it, sorry, with X squared YZ, XY squared Z, and XYZ squared. So this should be equal to, okay, so I'm covering this up and I'm doing this here. So what is the partial with respect to Y of this? What do you get there? Partial with respect to Y of this?
XZ squared.
XZ squared. Subtract from that what you get when you do this right here, which is the partial with respect to Z of this, which should just be XY squared. So that's your first component. Okay, the next component, you cover up the middle and you do partial with respect to X of this, which will be YZ squared, minus, now you're doing these right here, this one and this one. So partial with respect to Z of that, which is going to be X squared Y. But remember, you have to make the whole thing minus. Then the last one, you cover up this and you do your little determinant here. So partial with respect to X of that is going to be Y squared Z, minus partial Y with respect to that is X squared Z.
I have a question. Are we
Yes.
assuming that our vector field F is a conservative vector field always for this,
Nope.
for this curl? No?
Nope.
Okay.
Mm-mm. That's a good question, though. I mean, we can calculate the curl of any vector field. It will be interesting to maybe ask the question, you know, if it's conservative, then maybe the curl always gives you the same answer. I don't know. Maybe we'll see. All right, so that is just the mechanics behind calculating the curl. Now, let's find the curl at a specific point. So if we go to 2, 1, 0 and replace those in here, then we'll have, let's do it for this one, for this specific problem. So at 2, 1, 0, we would get a vector Okay, if I replace 0 for z here, let's see, -2, I think you get -2 here for the first one. Z0 going to kill that off. Let's see what we get here. 4, -4. So I think we get 4 in the middle. And the last one we get 0. Okay, so look, if you were to go to this point, 2, 1, 0, right? In 3-dimensional space, first you would have a vector at that point. This would be the vector at that point, whatever this is. Actually, what is the vector there? Be 0, 0, 0, wouldn't it? Be the 0 vector. But your curl at that point is this vector. Okay, so you know, what does the curl represent, right? That would be the natural question. What does the curl represent? All right. So in all of my notes that I have for my different calculus classes and all the different math classes that I've done, this was the hardest thing for me to ever code in this program is the curl. All right. So I'm showing you here in this 3-dimensional picture a point in space, okay? Here's a point in space, and the red vector represents the vector field. Let me see if I can zoom in on this. So the red vector represents the vector field. So if you were standing at that point, the red vector would be showing you the direction that you would want to move, okay? Like a flow. So if that were like a particle, let's say this is a molecule of water in the ocean, right? Just floating around in there, moving around. Then that red vector shows you the direction that you would want to move to next, all right? And the length of that vector would represent like how fast that particle or that molecule is moving. The curl, I have to animate it. The curl is the green vector, okay? And that shows you, if you were that molecule, you want to move in the direction of the red, but the green vector shows you an axis of rotation that you're spinning. So think of it really like a molecule. So the molecule maybe wanted to move, let's say, straight towards you, right? Like this. Maybe it's wanting to come straight at you. But as it's coming straight at you, maybe it's wanting to turn, okay? It's spinning, it's curling, okay? Curling through space. That direction of curl doesn't have to be, you know, like this. It could be like twisting with having an axis of rotation that's not even pointed towards the direction it's moving. And so the curl represents not only the direction or axis of rotation of the molecule, the length of the vector represents the speed of the twist or the speed of the curl. So let me move you to a different, like right now you can see my curl is a vector. Okay, here's the vector. And you can see that the curl is calculated by the computer to be the magnitude of the curl. The magnitude of that vector is 0.5. So what I'd like to do now is move to a different spot. There we go. Here's a different spot. Notice the curl got bigger. And now watch when I play it. Do you see how that's turning faster? So that little circle I have there is just to give you like a reference so you can see the twist. So the particle's wanting to move in this direction, but it's spinning almost like, oh, that's kind of cool. It's almost like this thing's coming at you, you know, going in a certain direction. It's almost tumbling over itself as it's going. Do y'all see that? And it's tumbling fast. You move to a different point. Let me get to a small curl. There we go. See how slow this one's rotating? So it's moving and it's just it's moving in a certain direction, just barely wanting to turn. Okay, so at every point in the space, all these molecules are wanting to move in certain directions and they have spins to them and stuff, right? That's what curl represents. That's pretty cool, right? Now, what about in two-dimensional space? Because we had two-dimensional vector fields, didn't we? We had two-dimensional vector fields. So what does curl look like in 2 dimensions? Well, we have a problem because in 2 dimensions, if you have a vector field, then how are you going to calculate this if it requires, because remember, cross products require 3-dimensional vectors. So how can you do curl that way? Well, there's an easy fix. All you do is you just call this vector field the vector field 0, negative x squared, and you just come in here and make the z component 0. And now you have a 3-dimensional vector field. Where the z component is 0, it's flat. And then you can still calculate the curl. So look at this. Curl is actually pretty cool to look at in 2 dimensions. Because on a flat sheet, you can look at the point here. I'm going to highlight it red. Let me see if it'll let me do this. So there's your point. These arrows are showing you the direction that that point wants to move, but the curl shows you what that point wants to do, twisting. So it's almost like if you were like this little molecule, if you put your hands out, then if the vectors on this side were pushing harder than these, then it would make you kind of like start turning as you're moving. So look at these little like paddle wheels. It's almost like catching the flow of what's around you. And right now, the actual curl is 0. I didn't realize that until right now. The curl is 0, which means the forces pushing on this side and this side are equal. So we have no flow, I guess you could say, or no twisting. Let me move us around. Oh, you know what? Look at this. Uh-oh, what's going on here? No matter where I go, the curl is 0. Let me do a different vector field. There we go. Here's a different vector field. Do you see the small little twisting motion I'm getting? If I move this thing over to this side, can you all visualize what's going to happen? See, the flow to this side is faster than the flow to this side. So if you stuck your hands out, you'd start spinning as you were standing there. If I go to the other side, now I'm going to spin the other direction. So curl, it kind of is what it sounds like, right? Here's another one, different vector field. I move up here. Kind of is what it seems to be. Oh, there's some really small curl. Okay. So the curl creates an axis of rotation, and the magnitude of the curl gives us the speed of the rotation about that point. If the vector field represents the velocity field of a flowing fluid, then curl measures the tendency of the fluid to rotate or curl at given points in the fluid. If the curl of a vector field is 0 at a point, then it is called irrotational. Hey, mini exam 6. I talk about this in mini exam 6. If the curl of a vector field is 0 at a point, then we will say it is irrotational at that point. And then this is what I said just a second ago. If our vector field is 2-dimensional, then it's easy for us to extend it into 3 dimensions by just adding a 0 for the z component. Now, do you recall from previous sections, and this is something we had talked about, I think, way earlier, the way you check to see if a vector field is conservative. There was a quick way we could check it, but it only worked if our vector field was 2-dimensional. And I said, we don't have a way of doing it for 3-dimensional. Well, it turns out that if your curl is 0 everywhere, okay, so if you calculate the curl and it's 0 everywhere, then you have a conservative vector field. So that's the easy check for conservative vector fields. Compute the curl, get the 0 vector. If you get the 0 vector, it's a conservative vector field.
I have a question.
Yes.
Since you can take the cross products for higher dimensional vectors, anything greater than 3, does that mean we could probably find whether it's a conservative vector field for any r to the n? Any, higher dimensional space, let's say we're working in 4th dimensional space with an XYZW component and stuff like that.
Yeah, we can extend this. It just, then your cross product is going to have to have a different definition because you now have more than 3 vectors, right? But there are similar ways to check for conservative vector fields for higher dimensional vector fields.
Okay.
Yeah. Now, okay, so you can check for yourself that if you were to take this right here, this vector field right there, PQ0, and you do the curl on it, you will actually get that to be true. And that's why for 2-dimensional vector fields, this is what we checked earlier. I think it's worth doing. Let's say I wanted to find del cross F. So I want to find the curl of F, which is this. And I'm telling you that the vector field we're talking about is only 2-dimensional, P and Q, but we add the 0 here. If I do this computation, I get partial with respect to X, partial with respect to Y, partial with respect to Z. And then here I have P, and then I have Q, and then I have 0, and I want to do my little determinant thing. So I cover this up. The partial with respect to Y of 0 is 0. And then partial with respect to Z of Q would be, so minus partial of Q with respect to Z. Okay, that, and then we have the middle one. So we cover that up, partial of 0 with respect to X is 0, minus partial with respect to Z of P, that will be what? Well, I'll tell you, it's like partial P with respect to Z, and put it there. Then we have to make that negative. And then the last one, cover this up. This is the partial of Q with respect to X minus the partial of P with respect to Y. Close the vector out. Close the vector out. Jeez. Y'all see that? But if this were a 2-dimensional vector field, do y'all agree that the P and the Q would only have X's and Y's in it? It would only have X's and Y's because we're in 2 dimensions. So this right here would be 0. Partial Q with respect to Z, there are no Z's there. And the partial P with respect to Z would be 0 also. So the only way that the only way to get this curl to be the 0, 0, 0 vector, to mean it's conservative, would be if that last piece was 0. But this last piece being 0 means that these basically have to be equal to one another, which is what we were checking earlier. So you didn't know why this was true earlier, but now you can say, oh, it's because the curl of a vector field that only contains 2 functions, P and Q, where they both just contain X's and Y's, well, then this is all that has to be true. And therefore, there's your quick check. I hope that makes sense. Okay, divergence. We'll pick up here. We'll pick up here. Yeah. So on that mini exam, let me just see what's there. I don't think you can do it all, but Okay, so as of last class, let's see, we can now do this. Is this a conservative vector field? Well, it's three-dimensional, right? Is it conservative? Well, check, right? Find its, oh wait, hold on, sorry, I misread that. It's telling you it is a conservative vector field. Find its potential function and then do this. Okay, now, next part, find this work integral over C, where C is this curve. A closed curve, right? Closed curve. This is a semicircle right here. It's a half circle right there. You can do this now. The last one, if this is a vector field, by the way, I'm missing a Z right there. That should be f of x, y, z. If this is a, yeah, just, you can find this part irrotational, but you can't do the incompressible yet. So let's say this. On this mini exam, I'm gonna make this due on Friday, because we will be able to talk about it on Wednesday. There's really only one part you can't do on this, and that's this. So after next class, you'll be able to do that. And then from there, I'll try and get another mini exam out for y'all, but you know, we're kind of at the edge of the notes here, so. All right, everyone, have a good day.
All right, have a nice day, sir.
Thank you, sir.
Thank you.